Hi, and welcome to everyone joining us today to discuss LFP and lithium metal anodes. I'm Tim Holme, co-founder and CTO of QuantumScape, and I'm happy to welcome you all to our webinar today. I'm joined by Venkat Viswanathan of Carnegie Mellon and Sam Jaffe of Cairn ERA to discuss the potential of LFP LFP being lithium iron phosphate, combined with a lithium metal anode, especially for EV applications, and to show how the QuantumScape cathode agnostic battery platform can enable this new paradigm, this new cathode. Before we start, I'd like to share that we'll post this webinar on our website at www.quantumscape.com. And of course, you can find it on YouTube on the QuantumScape channel after the event concludes today. So first, I'd like to introduce my friend, Professor Venkat Viswanathan of Carnegie Mellon. He's an associate professor in the Department of Mechanical Engineering. His research focuses on identifying the scientific principles governing materials design, inorganic, organic, and biomaterials, and novel energy conversion and storage routes. And also joining us today is Sam Jaffe, the managing director of Cairn ERA. Sam specializes in research around energy storage applications, technologies, and markets. And prior to starting Cairn Energy Research Advisors, Sam worked as an energy storage analyst. So we'll kick things off actually with Sam, with a few comments of LFP technology, its history, and why it is having a current resurgence.
Thank you very much, Tim. Appreciate it. And thanks for hosting this event and having me here. Really quickly about my company, Cairn ERA. We founded this in 2015. I've been in the battery industry for about 15 years. And the idea behind Cairn ERA is to do a battery and energy storage, electric vehicle and stationary storage, as well as consumer devices specific research and analyst firm. We do a lot of cost modeling of batteries, manufacturing process, as well as forecasting of battery markets. And we work with many of the largest participants in the industry, including many of the battery manufacturers, chemicals companies, and car companies that are in this space. Next slide, please. So what I want to talk about is just kind of putting LFP within its historical context, its own history, as well as within the battery industry itself. I think if I got a comment about 2 years ago from a client saying, hey, what's going on with LFP in China? Things are really picking up and there's a lot of interest there. And my response was, no, it's not. It's a dying chemistry. It's going away. It's not energy dense enough, and it's being superseded by everything else. That is not true. I was wrong. LFP is the phoenix of cathode materials. It has risen from its apparent death spiral and has become, yet again, a major contender within the battery cathode space. And I want to talk a little bit about why that is and why people were down on it and why it's become exciting again. Of course, LFP came out of Dr. John Goodenough's lab at University of Texas in '97. It had a lot of reasons to be excited about it. If you look at the molecular structure of it in that image on the right, it is a solid, bulletproof material. It is like a big iron cage where the lithium ions can go in and out through the channels within that crystal structure, as opposed to most other cathode materials, which are essentially layers on top of each other. Think of a game of Jenga where the lithium goes into the empty spaces there. But it does have some issues too with that crystal structure, which I'll get into in the next slide. Of course, at the time, what was exciting about it, because we were really living in a lithium cobalt oxide world, was there's no cobalt, which is still an exciting thing. But it's not just that, it's a low-cost material. You're really talking about iron oxide and phosphoric acid as your main non-lithium inputs into this material. And assuming you can make it at high quality and a low cost processing method, it is a cheap material. It has a reasonable specific capacity, a practical specific capacity of around 150 milliamp hours per gram, which translates into it's a low energy density material, 120 to maybe 150 watt hours per kilogram. in its current state, but it's good enough. And of course, it has much better resistance to thermal runaway, which has a lot of implications. It is an inherently a safer battery chemistry than others. But because of that thermal tolerance band going wider, you can actually make a larger format cell more safely. And that has a lot of implications too. Good. On the next slide, so what are the problems and how have those problems been solved? So I mentioned earlier that there's issues with the molecule itself or the crystal itself. How the number one was low electrical conductivity, and Michel Armand solved that when he figured out how to coat it with carbon to boost the conductivity. Again, the going down onto the crystal structure, it leads to a low tap density material. There's a lot of pores when you're putting these particles together. New milling techniques have improved that. Lithium iron phosphate is a low voltage chemistry. It's lower than the high nickel content chemistries. So how do you solve that? You don't. You run your head into a brick wall because frankly, that's just physics. But all of these things lead to poor volumetric energy density. And I think what QuantumScape will be talking about is their work on a potential solution, not solution, but a potential improvement in that area, which is essentially let's shrink the anode. The cathode is we're hitting some floors, but if you can shrink the anode, the volumetric energy density improves. And shrinking the anode means going to a new anode material. Lithium metal would be ideal. Similarly, if you get to lithium metal, you have a better voltage match with the LFP, but you also have, one of the issues with LFP is there's a voltage cliff at the end of discharge, which if not handled properly by the battery system, will lead to lithium metal plating within the graphite. Doesn't matter when plating is what you want. That's what a lithium metal battery, anode battery does. It plates lithium. Next slide, please. So what does this lead to? Being able to have a better LFP battery, I think the numbers, let me give you three numbers. $5 a kilogram. If I model out an ideal manufacturing process and historically accurate pricing for the input materials, you should be able to eventually get to $5 per kilogram for the LFP cathode powder. We're not really there today, but that's where you could get to. What does that translate into? Translates, I can model out a $75 a kilowatt hour battery pack for a car. And if I can solve enough of the volumetric energy density problems, I can make that car a 300-mile or 500-kilometer range car potentially. And what does that equal? A $20,000 high range car, which is essentially equivalent with the best option for a low-end internal combustion vehicle. LFP already dominates the very small cars in China, such as the Hongguan Mini, which is the best-selling car there. But getting it up, it's now getting into the mid-range cars, such as the Tesla Model 3 that's made in China, which is essentially a 400-kilometer car. So we've gotten to that point. And what's next is getting to the next level of range, which in my opinion, you get to 500-kilometer range car, and you're there. You're there at parity with internal combustion vehicles. On the stationary storage side, it means that you end up with an industry that will soon be completely dominated by LFP. Almost all installations, assuming that the buyers have access to LFP batteries, almost all installations will become LFP installations, in my opinion. Even something like micromobility, which in our forecasts will become the third largest market for batteries after cars and stationary storage. Even in micromobility, you start to open up a lot of vehicle types to LFP if you can improve the volumetric energy density noticeably. So even that will open up. And on the next slide is our overall forecasts for LFP versus other cathode chemistries. We're expecting 2.7 terawatt hours of lithium ion to be produced in the year 2030. And we're saying that 38% of that will be LFP. And as I said, this has been a declining space, the LFP space. Part of that is that LFP is a Chinese chemistry today. It will not be in the near future. It's expanding to production in the US and North America, in North America and Europe. But as more cars come online that are non-LFP, that's why you see that shrinkage. But starting in 2023, we will start to see the phoenix rising from the ashes of LFP getting back into contention and becoming a major part of the battery space, as well as becoming a significant answer to an area of of transportation and stationary storage that simply is not addressed today with current technologies. So I'll stop it there and turn it back to you, Tim.
Great, thanks a lot for the introduction, Sam. So I'll hope to expand on a little bit of what you're saying, but first the legal stuff. My presentation will contain forward-looking statements that within the meaning of the US security laws, and it means it includes data analysis and projections and models based on our current expectations. These forward-looking statements involve significant risks and uncertainties that could cause the actual results to differ materially from expected results. And further information about these factors that could materially affect QuantumScape can be found in our filings available on sec.gov, including the risk factors section. Okay, so from our perspective, what we're seeing are two, among several other industry innovation vectors, two that we're here to talk about today. On the anode side is lithium metal, and QuantumScape, along with many other players, are trying to commercialize a lithium metal anode, with the main objectives being to reduce the cost, volume, and mass of the battery, increase the specific energy and energy density of the battery, and also reduce the charge time. And then another significant vector on the cathode side, as Sam was mentioning, is LFP. Some of the drivers there is securing supply in high quantities. And then it's also been enabled by some cell design improvements and cell to pack innovations, or structural cells. So we'll talk a little bit more in detail about both of those, starting off on the anode side. So on the left-hand side, you've got a schematic of a lithium-ion battery. You'll have a host material here that includes graphite and often silicon, a porous polymer separator, and a cathode material. This could be LFP, it could be other nickel-containing chemistries like a nickel cobalt aluminum or nickel manganese cobalt materials, and the whole thing is immersed in a liquid electrolyte that conducts the lithium ions back and forth. Lithium, of course, is stored in the anode when the battery is charged, and as the battery discharges, lithium moves down into the cathode. And then the anode-free lithium metal battery, what it would do is replace this anode host material with nothing in the as manufactured state. And then all of the lithium that's present in the cathode as manufactured on the first charge would plates become a solid lithium metal anode. And then that is the lithium that gets cycled back and forth as the battery charges and discharges. So one thing that you can see from these schematics that are drawn roughly to scale is that by eliminating the anode host material, you really do make a meaningful improvement in the energy per volume of the battery. That also translates to energy per mass to some extent. But you not only improve in energy density, you can also improve in a lot of the other metrics that are really important to an EV driver or a battery consumer. Fast charge, so by eliminating the lithium diffusion bottleneck into the anode host material, you can enable faster charging. It also turns out that the anode is responsible for one of the main degradation mechanisms in a battery. So the reason your phone doesn't last as long today as when you bought it is in part due to the fact that the anode on every cycle can crack some of the protective layers that form around the anode and then have to reform, which consumes electrons and lithium from the cell. And so by eliminating that failure mode, you can also improve life of the cell. In terms of safety, by eliminating some of the flammable components and the organic separator that could melt and separate and expose more contact between anode and cathode in a thermal runaway event, you can replace it with a solid that's stable to very high temperatures and doesn't melt in most conditions. And then in terms of cost, you can also eliminate a whole set of manufacturing steps and a whole set of materials from the bill of materials of the battery. So these are 5 of the real key metrics of interest to batteries and especially to an EV, and all of them could be meaningfully improved, we believe, with a lithium metal anode. So then to come back to the cathode, so as Sam introduced, this is the crystal structure of lithium iron phosphate. What you can see is these ion channels in green here. Lithium is illustrated in green. As you look at this crystal structure, what you can see is that there are these one-dimensional pathways for lithium. So imagine driving your car on a one-lane highway and trying to get anywhere fast. You're going to go as slow as the slowest semi truck on the road. So that is one of the problems in this material. And then in addition, the electronic conductivity in this structure is fairly low. So both of these limitations need to be addressed and have been addressed in large part by making smaller particles so that the transport pathways are shorter, coating, especially with carbon, and then third, some metal doping. All 3 of these can improve the ion and electron transport through the structure. Cost, as Sam was outlining, is really a key reason, one of the key reasons for the interest in LFP. From just an active materials cost per kilogram, lithium iron phosphate is quite a bit cheaper than even a low cobalt NMC kind of a cell. And then along with that, the abundance of iron is very large. There are already, there's a lot of reserves of iron in the world. There are mature supply chains to extract iron for the steel industry. So very secure supply chain. And one thing that's changed, you might ask, well, things like the cost of iron hasn't materially changed in the last few years. What has changed that's driving the resurgence of interest in LFP? One explanation or one contributing factor is that the demand for batteries is now pretty clear is going to grow very quickly in the coming years, and the supply chains for materials like nickel and cobalt, while they're ramping up, it would be very convenient to bring another mature and large supply chain like iron on board to help through the scaling of the next few years. LFP, as Sam mentioned, has improved safety properties as well. There's less oxygen release from the LFP crystal structure at high voltage. In an overtemperature event, there's a higher onset temperature for exothermic events. It's a slower exotherm and also less heat generation. So if there is an overtemperature event or a safety event, as there will be in cars that crash, it's fundamentally a safer chemistry. This slide is one way to illustrate this. This is an accelerated rate calorimetry test where 4 different cells, these 2 green ones are LFP-based cathodes. The 2 blue ones are more nickel-based cathodes. The cell is placed into a thermal chamber. The temperature is increased. And then no further heat is put into the system, and you measure how much the temperature increases in the cell. What you can see is as you get to some point, once you've increased the temperature of the cell to between 150 and 200 degrees Celsius, the cell can go into a self-heating mode where not much additional heat is added to the cell, but it can self-heat. And that's what these lines that take off show. However, as Sam also mentioned, the energy density of LFP is lower than NMC. And that really comes down to a product of voltage and capacity. Energy density is really a product of the cell voltage times the cell specific capacity. So if you look at the voltage curve of LFP as it's discharged, it has that capacity of around 150 milliamp hours per gram and a voltage down here. Whereas NMC, especially as you charge up to higher voltages, can have higher capacities and higher voltage. So the delta that you're looking at is really sort of the area between these 2 curves, gives a higher energy density for NMC based cathodes. And so that's the reason why an NMC cathode will be prevalent in long-range electric vehicles on the road today. So this is another way to see the energy density landscape. On the y-axis is gravimetric energy density, so energy per mass of the cell, and on the x-axis is the volumetric energy per volume of the cell. And lithium iron phosphate is pretty significantly behind some of the nickel-rich chemistries. So that's one of the main reasons why you don't see LFP in electric vehicles that are long range in the West today. So it occurs to us that there's an opportunity to merge these two emerging vectors of lithium metal and LFP. And by doing so, you might address some of these limitations. So let's talk about that. This chart now plots energy density, energy per volume on the y-axis, and a continuous power density on the x-axis. So this would be a discharge over a long period of time, a substantial fraction of the battery's state of charge. And I'd like to point out 4 different curves on here. This curve in the lower left is what you'll see if you mix a graphite or hosted anode with an LFP. And as we've discussed, it has lower energy density relative to when you have carbon combined with NMC, which would sweep out this curve up here. The varying points on the curve basically is you can trade off in essentially any battery, you can trade off energy for power by varying the thickness of the electrodes, for example. So here we're just picking a few points on that space to look at the frontier of energy versus power. So then if you change this carbon host material to lithium for LFP, you can increase its energy density as well as the accessible power, just as you can if you replace the hosted anode for NMC with a lithium metal anode. You can also increase its energy density and power density. So I think that's pretty interesting that you could get the energy density of LFP into an interesting range relative to today's NMC cells. Then to come back to cost again, if you look at the cost of active materials here for NMC type cells, and you just add up the cost of the anode materials and cathode materials, if you switch to a lithium-free lithium metal anode, of course, you eliminate the materials cost of the anode. And so you can bring the cost of an NMC type cell down. You can do the same thing with LFP. So by eliminating the anode host material, you can also reduce its cost. Now, of course, these estimates are based, or these figures are based on active materials only. The active material is not the only component of the battery. So let's now talk about the inactive components. And here we're talking about battery packaging, the current collectors, the separator, any overhead space that has to be inside the cell to be packaged. So all of those materials, the current collectors, separators, cell packaging, include some cost. So if you put the cost of those inactive materials per volume on the x-axis of this chart, then you can translate the active material cost plus inactive material cost into cell cost. So this is a pretty interesting and on one level simple chart, although it illustrates something pretty interesting. So if you look at, if you assume that there's no inactive cost of the cell, then you're basically at the cell cost of raw materials, active materials only. And then you can draw lines out here that are lines of constant energy density of the cell, basically. Energy density per inactive material of the cell. And what you can see is that you can see a crossover between where LFP and NMC become the lower cost cell. So if you start off talking about a carbon NMC type EV cell, and you have expensive inactive materials, it is the lower cost material because you have higher energy density in the NMC itself. But over time, one of the other trends that has been changing is supply chains are ramping up. Manufacturing innovations are coming online that are reducing the cost of these inactive components. If they become low enough, the cost of the inactive components, there's a crossover between these two lines, and the LFP cell would become the lower cost per kilowatt hour cell all in. And so that's another one of these trends that I think people are anticipating, is writing these cost curves down towards the left. So this crossover point also occurs if you have a lithium metal anode. So if inactive component cost is high with a lithium metal anode and NMC cathode, the NMC is the cheaper cell. But as the inactive costs come down, there is also a crossover point where the LFP cell becomes cheaper on a dollars per kilowatt hour basis. So pretty interesting that you can reach a crossover point here, and LFP becomes the lower cost cell. So how does that change then the landscape of energy density that we looked at before? If you remove the hosted anode and go to a lithium metal anode, you can, as we've been describing, go to higher energy densities. And one really interesting takeaway from this chart here is you can take LFP into the range of today's commercial NMC type cells by replacing the hosted anode with the lithium metal. And of course, the NMC type cell will still offer the higher energy density, so it would be great for longer range cars. So the QuantumScape platform then is relatively agnostic. By developing a ceramic separator that separates the anode from the cathode, you can then anticipate using different cathode materials because you have isolated the anode from the cathode electronically and chemically. So we actually have done a little bit of early testing just to show that it could be done at a conceptual level. This is still early testing results, but it shows that you can have very, very minimal capacity degradation over initial cycling in an LFP cathode with a QuantumScape cell. So the rest of these test conditions are listed here. I won't go into every one of them, aside to say that this was an early test result done in small size cells, but it does illustrate the principle here that you can get compatibility. So just to sum up, what we've been describing is that you can shift this price performance frontier of LFP and NMC that we're on today, that using hosted anodes, down to lower cost and higher energy density operating points here by using this lithium metal anode. So with that, I'd like to conclude my prepared remarks here and turn it over to Venkat.
All right, thanks, Tim. Yeah, happy to participate in this exciting event where we're talking about sort of, I think the resurgence of the iron age. We wrote a preprint ahead of this this event where we analyzed with two of my graduate students, Shashank Sripadan and Alec Bills, the techno-economics of lithium metal paired with LFP cathodes. And I think one important point to note here is that lithium metal can come in two flavors. The flavor that we've discussed here, which is the anode-free configuration, in which the lithium metal is plated on the first cycle. And the second configuration, which is also another approach being pursued widely, which is to have a preformed lithium foil on the current collector, copper, and use that lithium foil in a lithium metal LFP battery. I think the interesting thing that we find, in congruence with what Tim and Sam have talked about, is that certainly it brings lithium metal, pairing lithium metal with LFP, brings LFP as a cathode much closer to the layered oxide. So I think that's widely clear. I think one thing that is interesting in terms of the cost aspect of those two configurations, that is using lithium foil, typically with a conventional separator, polypropylene separator, and a liquid electrolyte. The lithium foil there is needed typically because the electrolyte is being consumed quite a bit more than when you have a protected lithium anode like what is shown here. So in that case, typically the lithium foil is another sort of ingredient that adds to the cost, adds to the active material cost, unlike the anode-free configuration where you don't have any of the sort of anode cost. And of course, as a result, the associated plant area goes down. What we find from the analysis is, I think you can certainly make an extremely cost competitive lithium LFP cell, which I think now simultaneously addresses sort of the market and problem, which is that you want sort of low cost as well as high performance so that you can have long range and high energy efficiency vehicles, as well as meeting the sort of consumer price point of something in the $20,000 to $25,000 range. But I think all of this critically hinges on two factors. One, in the case of the anode-free configuration, it depends on critically on the cost of the separator. And then in the configuration with the lithium foil, the cost of the lithium foil is what predominantly determines how much cost savings you may have or not. And so I think, we're in a sort of great decade ahead where these approaches are going to mature, and I think there are sort of various shots on goal with lithium metal. I think the critical piece here is which of these configurations wins out will critically be sensitive to the price points that these components can reach. And so maybe I'll throw a question back to Tim. As a lithium metal component developer, can you share some insights on what you think are the projections for cost levels of the separator?
Yeah, so I think they clearly need to become in the same range as today's conventional polypropylene separators, in both their thickness and their cost for the whole cell to become cost competitive.
Yeah, and one other aspect that I think in that article we've discussed is, I think there are options for other anodes, right? I think there is another trend that another vector that, as you mentioned, Tim, is the growth of silicon, right? I think silicon anodes are certainly another extremely interesting and compelling option for improving the energy density of anodes. I think I want to throw the question open to both Tim and Sam, and of course I'll chime in with my own thoughts. What are your thoughts on pairing silicon anodes with LFP?
Yeah, interesting topic. I think from a cost perspective, silicon is in most approaches going the wrong direction. What we saw in Tesla's battery day, they outlined a few different approaches to silicon, and one was low cost, the others were high cost. So if you're going for a low cost cell, all the components need to be low cost, so that you'd have to pick a variety of silicon that's low cost. But I think even more problematic for pairing silicon with LFP is voltage. So silicon comes along with a voltage penalty. LFP already has a lower voltage, as we've discussed. So adding silicon is kind of a double whammy there. I'm not sure that silicon is a natural partner of LFP.
Yeah, and I don't think we quite got to that point in the discussions, right? That not only does lithium metal enable a more energy dense anode, but it also boosts the voltage of over graphite by a little bit. And of course, every little bit counts when you have a very low voltage cathode to begin with. And as you mentioned, right, silicon takes the voltage on the other direction. So I think certainly a very interesting trend to watch out for.
Yeah, well, so you raised the question of other anodes. Let me throw it back to you with other cathodes. So suppose you have a platform that isolates the anode from cathode. Are there other cathodes besides LFP that you think would particularly stand to benefit from this solid state lithium metal platform?
Yeah, so one that, a market that I am extraordinarily passionate about is aviation, where weight is everything, right? There, certainly, LFP is not going to cut it. There, you want to use as high a specific energy cathode material as possible. And I think there's an exciting opportunity around using conversion-based electrodes based on fluorinated electrodes, either metal fluorides or other kinds of fluoride-based electrodes that I think would represent a step change. And I think like how lithium metal has enabled LFP to sort of become very attractive. The interesting question then arises of what new cathodes that previously were not compatible with the ways in which we were thinking about the anode, what new cathodes can we enable? And I think the market on the other end is, there is an unlimited need in terms of specific energy, right? If you have a specific energy of 600 watt-hour per kilogram, then you will start to unlock more of the urban air mobility market. If you have a cathode that gives you 800 watt-hour per kilogram, then you'll unlock regional aircraft. If you have 1,000 watt-hour per kilogram, then you'll unlock other aspects of single aisle aircraft. So I think there's a long road on the cathode ahead for beyond today's layered oxide. So I think pairing lithium metal with those represents to me the most exciting frontier for next generation batteries.
And there could be other areas too. I mean, beyond the conversion cathodes, there's the high manganese ternary cathodes that potentially, the entire electrochemistry of the cell could change when you move to a lithium metal or certainly to a solid state environment. So one of the interesting things about this is nobody really looked at LFP with lithium metal 5-10 years ago, because everybody was obsessed with the high nickel. And suddenly you turn to it and you're like, wait, there's a lot of interesting convergences here. And that, we could start seeing similar things with all of these other cathode materials that we're discussing.
Yeah. And another reason that people might not have thought to pair lithium with LFP is that crossover slide that I was trying to explain, where if people thought of lithium metal as a high cost system, it wouldn't naturally pair with a low cost LFP. But if you can bring cost down in a lithium metal system, and by eliminating the anode, if it is the lower cost system, then it actually turns into a natural pairing with LFP.
Yeah, I think that's the underappreciated fact, right? Because your initial knee-jerk reaction to lithium LFP is it makes no sense, right? It's like you're pairing the most premium anode with like the cheapest cathode, right? What are you trying to do, right? But I think the key here is the premium anode actually comes at low cost if you can enable the anode-free configuration or with the cheap separator, or have very, very low cost anode foil, right? So I think the fact that the premium anode now comes with low cost, I think, reimagine sort of what we can think of as possibilities on the battery side.
Yeah, good point. Sam, do you want to follow up on any other application areas that you might see opening up if you could get a lower cost system into the market?
Yeah, the Model 3 made in China standard range car was not, that wasn't supposed to happen 2 years ago. I mean, they turned that around really quickly. They did so mainly because they had supply chain issues with their battery suppliers for their nickel batteries. But what they proved was you can get to a 200-mile car with LFP, and that's very significant. Now, the Model 3 is not a mass market car. It's still essentially a luxury vehicle, but getting to that next stage of getting into that kind of Toyota Corolla type of car is now open. It opens up, and that's one of the interesting things about this, is that this isn't necessarily you're not really leapfrogging anything or completely displacing the nickel market. Nickel batteries are here, and they are here to stay, definitely. But what it does is it opens up spaces in the application categories that simply could not be addressed in the past, such as a moderate range car, affordable car, or such as a lower end e-bike battery pack that's good enough, as opposed to an e-bike that might just simply be priced out of most people's capabilities. And on the stationary storage side, there's a convergence of factors that opens this up that open up a lot of applications of what you can do on grid management with a battery that you couldn't really affordably do before.
Great. We haven't talked too much yet about cell to pack, or these large structural cells that are emerging. I don't know if any of you have comments or thoughts on why LFP is appropriate for these types of designs.
Yeah, it's critical. It's critical for these cost reductions and getting down to that $7,500 or even $75 kilowatt hour pack level costs. If you open up a Nissan Leaf made a couple of years ago, it's these huge metal boxes with batteries inside. Each module is encased in these very large aluminum and steel structures for safety reasons, for management reasons, et cetera. And if you can just make the battery cell the module, you save a lot of that other stuff inside the battery pack. But you can't do that if the cell's too small, first of all. You need a big cell, and you can't do that if it's not safe. And that's where LFP really plays a role, because it opens up the possibility of a very large prismatic battery, meaning a metal cased battery. It doesn't have to be cylindrical, it can be rectangular, but a very large battery. And the reason why we don't do that in the past is the bigger the battery, the more thermal mass you have when bad things happen. And then the temperature turns into a fire. When you have more tolerance for that, you can get to a higher thermal mass, which means, hey, I can make the battery bigger. And with a prismatic battery where the case can become a structural component, suddenly you start to make this cell to pack technology reasonable. And if you look at the BYD blade pack, that's exactly what they've done. They're very big, very long prismatic batteries just stacked right next to each other. There's another layer to that though. And Tesla talks about the cell to vehicle concept. And again, you can eliminate steel in the chassis of the vehicle if this battery becomes a strong enough structural component. It's really hard to do that with a small battery. So if you can go to bigger, if temperature tolerance allows you to go to bigger batteries, you can cut costs not just in the battery pack, but in the car itself.
Yeah, and I think one notable thing on that same thing that Sam mentioned is in this paper by C.Y. Wang earlier this year, they actually compared all of the sort of gravimetric cell-to-pack efficiency, and the BYD blade, both on the gravimetric basis and a volumetric basis, especially on a volumetric basis, is unbelievably good, right? I think it's really amazing to see cell-to-pack engineering giving you so much benefit, and ultimately, at the end of the day, the consumer cares about what's the efficiency at the pack level, right? Not at the cell level. So from a consumer standpoint, that is a critical factor. And so the synergies are certainly causing LFP to really rise to the top.
Yeah.
Tim, maybe I'll throw
one comment before you say, from a material scientist perspective, it's kind of sad to see you perfecting these perfect little crystallites of active materials, and then to see how much that gets diluted by things like steel and packaging, both at the cell level and then the module level and then at the vehicle pack level. So once you break it down, what fraction of the mass or volume of the overall car or car pack is the active materials that are actually storing energy? It's a depressingly small fraction.
My precious powders are being diluted.
So if you are able to eliminate some of the steel and structural components of the battery pack and make more of it into the active materials, that's certainly a benefit.
The extreme version of that is what is there in aviation, right? True Blue Power sells the same nanophosphate LFP pack at 64 watt hours per kilogram, right? So, you start to cringe when all of that weight goes into the metal. One thing I wanted to make sure we touch on is around why 2021 or why 2022 is a very important period in the journey of LFP. Which is around the sort of intriguing patent wars associated with the LFP. So I'm curious if one of you can comment a little bit on that.
Yeah, I followed it a bit. So patent law is perhaps not the most compelling subject, but it is quite interesting that there have been real meaningful lawsuits in the LFP history. But why these years are now significant is that a lot of the key early patents in LFP technology are now expiring in, now plus or minus a year. There are 3 key patents that are expiring. These were some of the earliest patents on the material itself and then how to coat it with carbon to make it work effectively. These patents are all now expiring. Previously, there was a consortium created to license the patents out together as sort of a package deal so that somebody making LFP could get a license and make and sell LFP. These patents were enforced in the West, and so licenses were given in the West, but they were never really applied in China. So what that means is that Chinese LFP was always able to compete effectively at essentially a price discount relative to LFP anywhere else. And that is probably one of the contributing factors for why LFP was a larger technology in China than it was in the West. So as these patents expire, that sort of extra price premium for the license will go away. And I think that'll allow the Western LFP makers to then compete on a more even footing with the Chinese LFP makers.
One other point about that beyond the patent space is in the fact that the LFP today is essentially a Chinese industry. You do not buy LFP from anywhere else but China today. Is that as we get to these very low cathode prices of this, $15 and below per kilogram, the cost of intercontinental shipping of that bag of cathode powder starts to become more and more of a proportion of that overall cost. So outside of patent issues, outside of tariffs and trade war issues, it's going to become very important to establish an LFP supply chain and battery manufacturing capacity on each continent. And that is happening. And again, back to your point about why is this period critical, is we're in the midst of an enormous manufacturing boom. And part of that is going to be producing LFP batteries in Europe, in North America, in India, in other places beyond just China.
Maybe I'll throw out one provocative question that has been sort of a large thread in our Slack workspace, is around making a projection for 2030, right? So of the share of LFP batteries that are deployed in 2030, so new batteries deployed in 2030, what's the share of that paired with graphite? What's the share of that paired with mostly silicon? And what's the share of that paired with lithium metal? So there was a sort of a several hundred message thread with a lot of sort of leading people, Dan Steingart, Steve Harris, many others that have made projections. I'm curious what you both think about that.
Sam, you had a slide where you were projecting LFP forward. Do you want to take a crack at that? I'd rather stay out of this business of making predictions about the future that are going to certainly be wrong coming from me.
So in terms of the anode matching, we're not really forecasting by anode cathode match. What I will say is that in our forecast, we respond to what's happening in the marketplace as well as what's happening in the laboratory. And that proportion of next gen anode materials, how much of that will be sold is, the people that have the biggest say in that are Tim and his colleagues in the space at QuantumScape and elsewhere. If this turns into a truly mass manufactured product, it is extremely disruptive and will change forecasts considerably. Yeah,
so I have been asked to make my statement, which I had made in the Slack workspace. So I will state my ratio, which was of the LFP batteries sold in the automotive space in 2030. My split was a 3-to-1 between lithium metal and graphite. So we'll see if. It's another wrong prediction that we'll see how wrong it'll be. So it's an exciting time to watch.
Well, I can tell you that I and my coworkers here are going to be trying very hard to meet or exceed that number. We'll see how far we can go, but of course we'll be supporting both NMC type nickel rich materials as well as LFP, and be guided mostly by our customers as to our split there. Yeah. So one concept that I don't think has come up yet today is second use and reuse and recharge and recycling. So of course, one of the concepts that got me most interested in batteries in the first place was we wanted to move from single use petroleum to rechargeable batteries and renewable energy. And so if we use the battery and then throw it away, of course, we're only taking small strides relative to what we could do if we used the batteries in a second life or recycled them. Do either of you have comments on second life or recycling of LFP especially?
LFP creates a tremendous problem for recycling, because you take out the nickel and the cobalt and the value of that material inside the battery becomes a lot less exciting to recycle. In fact, it's in most cases negative. Most papers that I've read that try to figure out the actual value of the materials coming out of the recycling plant, you're losing money recycling LFP. Now, which makes the importance of repurposing even greater. Repurposing is a very misunderstood topic, and it's really, really hard to get a lot of people, a lot of utilities and energy developers to buy repurposed batteries, no matter what, because there is a safety component. 10-year-old battery that you don't know exactly what happened to that for the last 10 years is a big safety liability. LFP has a better profile for that because it is going to last longer, and because if safety events occur, the thermal runaway issue is less. So what I expect to happen is that we'll see more repurposing of LFP transportation batteries than of the other batteries, and longer lifetimes in the stationary space. And then when recycling, it's really going to have to be more of a regulatory issue than a purely economic decision. If we leave it to an economic-based decision to recycle LFP, it won't happen a lot. What are your thoughts on that, Venkat?
Well, yeah, there are two things that make me a little bit even more optimistic than what you said, Sam. First is that because the LFP particle degrades so little, that even though there's less value in it than in one that contains nickel or cobalt, that it might be conceivable to actually just recover the particles and reuse them without further processing, without breaking them down into constituents and reforming them.
And you think there's a better chance to do that direct recycling with LFP versus other cathode chemistries?
Yeah, if you look at an NMC, you do have over life structural changes. There's oxygen evolution. You can form rock salt on the surface layers. LFP is a much more bulletproof particle. So I think I don't know how close we are to actually just turning those particles directly around and putting them in a new battery, but I think it is more hopeful that you could do that with LFP. And the second thing that makes me a little bit more optimistic on reuse is that I think battery makers are going to be collecting a lot of data of the batteries in the field. So, once you let an electric vehicle that's a tens of thousands of dollar product out into the field with expensive batteries in there, it's pretty cheap to put a little bit of telemetry in the package as well and send back all the use data, and then storage is of course cheap too. So I think it's not far-fetched to think that almost all EVs would have their data, all the usage data stored, and so you would know with some granularity each battery, how it was used, what its current state of health is, and so then it becomes easier to do the repurposing. But Venkat, what are your thoughts?
Yeah, I think that last point is very important, right? Which is critical to the cell repurposing or cell recycling. Like you have to, at the end of life, make a decision. And in order to make that decision, you need data to make that decision, right? So I think your point that every battery will have a cell history, right? Or every cell and every module and every pack will have its own cell history recorded. I think that's going to be a critical piece to repurposing and recycling. I think data and machine learning, of course, is going to sort of fundamentally alter how we use and manage them. So I think recording this data, we should actually do much better than we are doing at this point. I think there's not enough monitoring enough monitoring and of course exporting of that data out around batteries that needs to get better. And I think this is making the case for the forever battery even more, right? I think if repurposing is the only way to go, right, then we just need to get really, really good at making the cycle life so long that basically, where it's well beyond the usable life for one product, right, that then you can seamlessly move it to the next space. So I think all that produces the right kind of technical challenge for the material scientists listening, right, to go and bring that degradation down as much as possible.
Great. Well, listen, we're coming to the close of our hour here. So before we sign off, I'd like to give you both a chance to provide some final remarks or takeaways for our audience. So Venkat, let's start with you.
Yeah, I think this is a very exciting space. I think I think there are many many vectors all pointing in various different directions, and progress happens when they all sort of align. And I think in this case, we have sort of two vectors in alignment here. I think this is a very exciting period for both lithium metal and LFP. And I think, Sam sort of at the beginning alluded to this. I think what might be possible with lithium LFP is sort of a creation of a market that is where you have a car with, he said it in kilometers, so I'm going to say the same thing in miles, right? So something that is about 360 miles, right? And the reason I picked 360 is people usually charge up to 80%. That means that usable range is about 300 miles, right? So I think 360 is a nice round number in my head. 360-mile car that basically can be at a price point of $20,000 to $25,000. I think this is a sort of new frontier that can be enabled in the next decade with lithium LFP. I think this is a very exciting opportunity and sort of really creates a new market that I think will simultaneously be both long range and sufficient range such that addresses the sort of consumer range anxiety issues and sort of, knocks that out completely, as well as is at a price point where I think it is compelling for them to choose this as the default buying option.
Great, thanks, Venkat. Sam, what are some key takeaways?
One thing we haven't talked about is supply chain. And within the battery industry, there's tremendous stress today on the supply chain, both from a battery manufacturing point and from the entire upstream supply chain. When you talk about LFP, that gets a lot easier to grow and to grow quickly and to grow sustainably. Nobody needs to build a new iron mine to supply enough iron, however many batteries are ever needed. There's enough iron. You could say the same on the phosphorus side. And then when you get into the processed chemicals, the supply chain actually gets narrower or I guess simpler in the sense that it's iron oxide is the usual input material, which is rust, and it's phosphoric acid or other phosphorus containing compounds, which are simple, basic commodity industrial chemicals that are widely used in many other industries anyway. So the ability to build this out on a continent by continent basis, from mine to car to stationary storage to recycling center, becomes a lot easier with an LFP with LFP. And that's important. That's really there's two challenges going forward over the next 5 years. One, as I said, Tim, is on you. Make this work. Take it from the lab to the factory. And two is, how do we build out the supply chain without, affordably and in an environmentally sound way? And in some ways, LFP makes those two things simpler.
Great, thanks a lot. I just add one concluding thought from the QuantumScape perspective. We've talked a lot about LFP today. I want to emphasize that from a QuantumScape perspective, we are pretty agnostic. NMC has a lot of its own benefits. We're still really focused on making the best battery. That's our mission here at QuantumScape, make the world's best battery, and we will be doing our best. So great conversation. Thanks a lot to my guests, Venkat and Sam, for joining us on the informative webinar. And thanks to the audience. I hope you all enjoyed it and learned something today.
Thanks a lot, everyone.
Thank you.